Alright, fourth gas law is the ideal gas law. And since we've worked with pressure, volume, and temperature, we're now going to add a fourth variable, and that's going to be our moles. And so the volume occupied by a gas at a specific temperature and pressure is going to be dependent on the number of gas particles that are there. Your moles of gas is going to be directly proportional to the number of particles, so moles are going to be directly proportional to the volume. Applying moles to our combined gas law, we end up with P1 V1 over N1 T1 equals P2 V2 over N2 T2. Since we can set PV over NT equal to each other on two sets of conditions, that means that it's going to be a constant, and it's going to hold for ideal gases only. Ideal meaning that they behave the way mathematically we would expect them to behave. So this constant is R, and that is the ideal gas constant. And there's two ways of writing this ideal gas constant. The first one is 8.31, and the unit is liter kilopascal over Kelvin mole. So this is the volume, this is the pressure, N is the number of moles, T is the temperature. So this is the unit for your ideal gas constant. It's coming from these four variables: pressure, volume, number of moles, temperature. So these four things are coming together to make this one derived unit. The other version is 0.0821, and you'll notice it's still in liters, it's still in Kelvin, it's still in mole. The only thing that's changed is the pressure unit, and so this gas constant is used if your pressure is in atmosphere. This gas constant is used if your pressure is in kilopascal. So after lots of rearranging, we come up with our ideal gas law. PV equals nRT. So this is the one you're going to have to use on problems, where P is your pressure, either in atmosphere or kilopascal. V is volume. It should be in liters. N is your number of moles. R is your gas constant. And T is your temperature. It needs to be in Kelvin. So let's say we fill a rigid steel container. It has a volume of 20 liters with nitrogen gas to a final pressure of 2.47 times 10 to the fourth kilopascal at 28 degrees Celsius. They want to know how many moles of gas does the cylinder contain. Well, first we need to make sure that our units are where we want them. And we have liters. So volume is the 20 liters. Pressure, we have 2.47 times 10 to the fourth kPa. Now here, our temperature is 28 degrees Celsius, but we need it in Kelvin. So remember, to turn this into Kelvin, we have to add 273. So 28 plus 273 is 301 Kelvin. So this is going to be the value that we use when we're solving our problem. And so they want to know your number of moles. So since we have PV, N, and T, that N is our clue that we're going to use the ideal gas law. So we have P, we have V, we have N, or we're looking for N, R. So we need to figure out which gas constant to use. And since we have kPa here, that means we're going to use our 8.31 liter kPa over Kelvin mole. So since we're solving for N, we're going to have to rearrange this for N to get N by itself, which means we're going to have to divide both sides by RT. So now just plugging in, our P is 2.47 times 10 to the 4th kPa times V is 20 liters divided by R. We said we're going to use 8.31 liter kPa over Kelvin mole, and our T is 301 Kelvin. So here's where writing your units comes in handy, because you can see that kPa over kPa cancels, liter over liter cancels, and Kelvin over Kelvin cancels. So we're left with moles in the denominator of a denominator, which brings it up to the numerator. And since we're looking for moles, that's the unit that we have left. That's what we want. So now we can plug in 2.47. Use your E key. Save you some parentheses. E to the 4th times 20 divided by 8.31 times 301. And using 3 sig figs, you should have gotten 197 moles.